note. Either is okay. Sometime this week is fine. It doesn't have to be necessarily next class or whatever, but like, you know, dawdle on it too bad. I'll ask you about it if you've forgotten about it. I have a million extra copies, so if you're like, oh no, I lost one. Come back and grab one. I have lots of extras. Looks like there's an unclaimed one from 4th hour yesterday. All right. Our plan for today, we're going to do sections 2, 3, and 4 in chapter 1. That'll be kind of 30 to 40 minutes probably. The second half of the period, I'll let you guys work on the chapter 1 homework set in class. Next class we'll do a classwork assignment, your first classwork assignment. And then the following class will be the chapter 1 test. So like, we're just ripping right through stuff. You'll see today that the rest of chapter 1 is like no big deal, right? Like none of these ideas are really complicated or difficult, even if some of them might be a little new. But we're, you know, living in pretty easy terms here. Okay. So section 2, we're going to talk about exponent rules and exponential functions. Again, this is something we probably saw dating back to as early as maybe middle school with pre-algebra. So we're just kind of, you know, starting from the real basics. So when we talk about an exponential function, we're talking about something that can be written in the terms a times b to the x, with the caveat that b can't be 0. Why do we disallow a to be 0? Well, if a is 0, the whole thing just zeroes out. It's a constant function, right? We don't want to define that as an exponential. And then we say b has to be positive and not equal to 1. So what happens if b is equal to 1? So b to the x just turns into 1, and 1 times a is a, and that's a constant again. We don't want that. Why do we require b to be positive, though? What's the problem there? Yeah, very good. So if we allow b to be a negative value, your x's could be things like 1/2 or 1/4 or 1/6. And remember, an exponent of 1/2 is the same thing as a square root. Exponent of 1/4 is like a 4th root. 1/6 is like a 6th root. So you have like all these discontinuities all over the place. This would be a terribly looking defined function. That's why we don't allow b to be negative. To get a nice clean exponential function, b has to be positive and not negative. From a vocab standpoint, oftentimes we refer to the a coefficient as the initial value, because when x is equal to 0, f of x is just a. We often call b the base, because when we see if I look at like the rate of change of the y coordinates, you know, one change in x is going to lead to a times b change in y. So each time you change x by 1, the y coordinate changes by a factor of b. So it's a multiplicative relationship. And that exponential functions have a horizontal asymptote at y equals 0, right? So if the base is greater than 1, the left-hand side, we have an end behavior as x approaches negative infinity, y goes to 0. Or if that's if b is greater than 1. If you have b less than 1, it's the opposite. It's going to be as x approaches positive infinity, the y goes to 0. But either way, you have that one horizontal asymptote for all exponential functions. And if it's written as this form, it'll be at y equals 0. That's all garbage. So that's just a reminder that when we're evaluating an exponential function, you have to follow the order of operations, specifically that exponents have to happen before you do multiplication. Right, so let's run through a couple of examples of this. If I have the function f of x equals 3 times 2 to the x, and I want to evaluate that when x is equal to 2, what do we get? 12, right? We plug 2 in for x, 2 squared is 4, times 3 is 12. Right, we're just kind of practicing using these order of operations and refamiliarizing ourselves with how to deal with an exponential. If we do the same thing, now x is equal to 0. We get 3 because 2 to the 0 is 1. We wrote anything to the 0 is 1. That's not quite true. There's one exception to that. What's the exception? 0 to the 0 is not, you can say undefined in this class, that's fine. Technically, it's something different than undefined. It's called indeterminate. It's kind of worse. What about if x is equal to -3? It's going to be 3 over 8. Right? The negative exponent makes a reciprocal, so 1 over 2 to the third, which is 2 to the third is 8. So 3 times 1 over 8 is 3/8. Always remembering this. We'll consolidate all these exponent rules in a future slide in one place. We're just kind of like doing some exemplar to kind of do some refreshing, right? This is all stuff we would have covered multiple courses. How about an exponent of 1/2? So x is equal to 1/2. What will we get here? It's going to be 3√2, right? Remember the fractional exponents are equivalent to radicals, where the denominator is the index of the radical. So we just have 3 times √2 or 3√2. Everybody's okay there? Okay. How about -3/2? This one's going to take a minute to sort through, right? Pretty unlikely you're able to carry this much through in your mind. There's a lot of stuff that needs to happen. So if I'm going to think about doing this, probably the first thing I'm going to deal with is the negative exponent. So I'd start by writing it as a fraction, the negative exponent. And then I have that 3/2 there, right? So I'm going to think about that as 3 times 1/2. Because I know that if I have multiplication in the exponent, that's like an exponent of an exponent thing. So I'm going to take the 3 and push it inside and the 1/2 on the outside. You could do the reverse, it's fine also, but you not as obvious what to do with that. 3 to the 8th, though, I know is, I'm sorry, 2 to the 3rd is, great googly mooglies, is 8. So I have 8 to the 1/2, and remember 1/2 is the same as a square root. And square root 8, that can reduce, right? How does that radical reduce? 2√2, right? I can think about 8 as 4 times 2, so square root 4, 2 times square root 2. So 2√2, and then I multiply the top and bottom by √2 to rationalize the denominator. And oh my gosh, is this thing still going? And we end up with 3√2 over 4. Unlikely to have been able to work through that in your mind without writing anything down. That was a big ask, Mr. Cooley. Come on. Maybe you would have gotten to 3 square root over square root 8. But like to do all that extra reducing and rationalizing, that's a lot to carry. Done, finally. So our basic properties of exponents. Found those guys out there for you guys. These should all look familiar, right? If we multiply two exponentials with the same base, we add their exponents. We divide two exponentials with the same base, we subtract the exponent. We have that exponent of a product, that exponent applies to both factors of our product. If I have an exponent of a fraction, it applies to both the numerator and denominator of the fraction. The negative exponent makes a reciprocal. That exponent of an exponent, we multiply the exponents. That a fractional exponent is the same as a radical. And, the 0 is equal to 1 unless it's 0. Right? So again, these things should be familiar. You should recognize those. It's like, okay, like maybe if you asked me to write down all the properties, I wouldn't be able to do it, but like I can do them when I'm doing the problem. I know what to do with it. That's good enough. It's not like this is gonna be a test question to like write down all the properties, like get out of here. And in general, the IB doesn't have a big penchant for memorization. If they want you to remember a formula, they're probably gonna just give it to you and then ask you to do something with it. That A and I for this course is like applications and interpretations. So the philosophy, what we're doing is like, here's some stuff, like do it and then tell us what it means. It's not gonna be like memorize this or derive that, or it's not that kind of a course. So reviewing to solve an exponential equation here. So there's a couple of different approaches you can take. I'm going to show you one approach and talk about what the second one would be in parallel to doing this. At least when they start to diverge. I mean, the beginning steps would be the same. First step here would be to divide both sides by 20. Excellent, right? We want to try to get that exponential piece by itself. So if we divide both sides by 20, 5 divided by 20 reduced down to 1/4. And now what I notice when I look at the left-hand side and the right-hand side, I have a base of 1/2 on the left and a base of 1/4 on the right. Well, it's possible for me to rewrite those so they have the same common base, right? 1/4 I can recognize, well, that's just 1/2 squared. Will that always be the case? Will I always be able to do something like this? Not without having to use a logarithm. I mean, you can always do this, but you have to use like a logarithm to do it, in which case, like, we do the alternative. Is everybody good with what I did there? Now, since the two things are equal and the bases are equal, what does that say about the exponents? They also have to be equal, right? Yeah. The two pieces are equal and their bases are equal, the exponent's got to be equal. And then I can just say x equals 6, right? Alternatively, at this step, instead of rewriting 1/4 as 1/2 squared, what else could we have used? To cancel out this exponent base of 1/2. What other tool could have we used there? A logarithm, right? We could do log base 1/2 to both sides and proceed from there. That's fine also. There's no preference to me which approach you take on a problem like this. You do whatever's most obvious to you or whatever you're most comfortable with is totally fine. The IB doesn't assume you know what a logarithm is yet in this chapter. Now I know you do because everybody comes in with, taking a pre-calculus course where it's for sure covered, and an Algebra 2 course where it's probably should be covered. A lot of schools will teach this as a 2-year course without a pre-calculus prerequisite, where they're doing the pre-calculus things that you've already done inside this course. So sometimes things are funny with the way they're trying to do things because they don't assume that you already know these you know, like what sine and cosine do, or, you know, what a logarithm is. So, as an aside, just keep in mind that anytime we solve an equation that's checkable, so you can check your answer to see if it's correct, is it required to check for an extraneous solution for solving an exponential equation? No. And the reason you know that is the domain for an exponential function is all real numbers. And when you translate that exponential function into a polynomial function, or polynomial equation right here, the domain for a polynomial function is also all real numbers, so there's no way to get an answer in the polynomial form that won't work in the exponential form. That is not true if you're solving a logarithmic equation, right? The domain for a logarithm is typically, you know, x greater than 0. When you translate that into a polynomial whose domain is all real numbers, it's possible to get answers in the polynomial that don't work in the logarithm. So those are situations where you have to check for extraneous. But that's the why sometimes we have to check for an extraneous and sometimes we don't. Is when you translate it to a polynomial, you have like a domain mismatch. All right. Yeah. Let me check. Okay. That's it for this section. Everybody's okay? Exponent properties. You could simplify an expression with some exponents in it. That's about the gist of it. And good review. And now let's do this one. So this is going to be sections 3 and 4 here. So section 3 is basically scientific notation, like how to put numbers in and out of scientific notation. The most confusing part of this is the way that the IB chooses to tell you to do something in scientific notation. So the IB language doesn't use the term scientific notation. They call it standard form, or they'll say standard form where, you know, a times 10 to the k, where a is between -10 and +10, which is just describing to you scientific notation, but it's like in the most confusing way possible because it's like super technical. Now, if you read that and you're like, oh, you're just saying scientific notation, great, but that's an uncommon presentation for where you guys are.
Wait, what do they say instead of scientific?
Standard form. Yeah. So again, changing a decimal from standard form, aka scientific notation. So if I say I have 5,120,000, I need to start by finding that value of a between -10 and 10. That's the 5.12, right? That captures all the significant digits. And then I am going to count how many decimal places I have to move the decimal to here. So 1, 2, 3, 4, 5, 6. So it means I'd have to multiply this by 6 tens. So there's my 10 to the 6th. Right, you guys remember I've done this, I think, again, it's some middle school introduction. You've probably done it a bunch of times in your science class or whatever. You can do the same thing with small numbers. And since we're moving the decimal point in the opposite direction, instead of multiplying by 10, we are dividing by 10. So in your scientific notation, your exponent is going to be negative. Feel okay with this? I think this is usually pretty straightforward, right? Okay. And then you should be able to go backwards from the scientific notation back to a standard decimal. So again, positive exponent. So I know I'm going to be moving the decimal point to the right. The number should be getting bigger. I'm going to move it 6 places and then fill in zeros, you know, for every decimal whenever I run out of integers. So 1, 2, and then I have 4 more spaces, so 4 zeros at the end. Everybody's good? This should be pretty easy, right? Nobody's hopefully too concerned. Same idea with a negative exponent, except this time which direction am I moving the decimal point? Left, and again, I'm filling in zeros after I run out of digits. So I move one digit for the 6, and then I have 2 more zeros, and then my decimal. Okay. That's it for scientific notation. I think that about does it, right? You guys feel okay with that? Like, there's not much to say. You've done it before. Yeah, it's literally like standard form of scientific notation. That's about the note that you need, right? And our last section here is about exponents and logarithms. So if you remember our basic properties of exponents that we looked at on the previous slide, it's the exact same properties you saw like 8 slides ago. The reason I'm showing you these is to compare them with our, in a moment, with our properties of logarithms and show that like, hey, this property of logarithms is just the logarithmic equivalent of this exponential property. So remember our basic definition of a logarithm is that if I have like log base b of x equal to y, I can translate that equation into a exponential equation that says b to the y is equal to x, right? The bases stay the same on the logarithm or the exponent, but the output of one becomes the input of the other, right? Is everybody okay with that? Remember this definition from your Algebra 2 or pre-calculus courses, I hope. So our basic properties of logarithms are things like any log of 1 is equal to 0. Log base b of b is equal to 1. Log base b of y is equal to y. B to the log base b of x is equal to x. And these are, if I do this same switcherooski to put them back into exponential form, you see that you get these basic exponential properties fall out. These are just the logarithmic equivalent of, b to the 0 is equal to 1, for example. Everybody okay with this notion? Again, of all of these things, the big thing to remember is that like any log of 1 is 0. Log base b cancels exponent base b. That's like what the third thing is saying there. Or exponent base b cancels log base b. That's like that fourth statement is saying. Right? Those are the kind of the big takeaways here from this. So a couple of quick definitions. There's 2 special logs that have a special name. The first one is the common logarithm. Common logarithm, we write just log with no subscript. We understand the subscript there to be 10. Just like when we write a square root, we don't write the index 2 on the square root. We just know it's index 2. Same idea here. Similarly, we have a natural logarithm, that's log base e. Again, we don't write log base e, we write the abbreviation ln. Typically, when I'm writing that on my paper, I'm going to use the script, like a cursive L, to write these things. Why am I using a cursive L rather than like the print L in a math class? To distinguish the L from a 1, yeah. Which again, like, depending on your penmanship can be an issue for some of us or not. I like to use cursive L's because I don't, same thing when I draw my Z, I put a bar through the middle to distinguish it from a 2 because those guys look pretty similar. All right. So a reminder on your calculator, on the left-hand side, built into the keys on your calculator, you have the common log and natural log on there. You can also access through the math menu. I think it's like command 0, it's down near the bottom in that list, the log base command where you can type in a log of any base. So let's do a couple of little quick practices here. So if I want to evaluate log of 100, first thing I want to do is recognize what the base of this logarithm is. Note that that's log base 10. And then you, for example, could use your property of, or your definition of a logarithm to rewrite that as an exponential equation. And at that point, hopefully you recognize that 100 is 10 squared. So x has to be 2. Right? Alternatively, you could work in here and say, okay, 100 is 10 squared, and then log base 10 cancels exponent base 10, and you're left with a 2. Think about it that way, it's equivalent way of thinking about it. Just whatever's more natural for you is fine. No big deal. Set that. Don't do that. How about log of the 5th root of 10? Who can do it in their head? Mr. Kulik can, it's one thing. So, to do that though, again, you can start by writing a logarithmic equation using our observing that this is log base 10 because it's the common log. Then use our definition of a logarithm to rewrite that as an exponential equation. Hopefully you see the 5th root is the same thing as the exponent 1/5. And at that point, oh yeah, of course, x is 1/5. Right? Alternatively, you could have worked all inside of here and just written this as 10 to the 1/5, and log base 10 would cancel exponent base 10, and you're left with the 1/5. Again, either work is appropriate. You're doing the same thing, just like with different mechanic, but it's the same properties, the same definitions. It's happening, so it's doesn't matter to me. So there we go. All right, keep going. Ooh, log of 1/1000. Who's got it in their head? Yeah, there you go. Love it. So again, start by writing it as a logarithmic equation. Note that the base here is 10, even though it's not written. Use our definition of a logarithm to do a switcherooski. I recognize 1,000 is 10 to the 3rd. And then because it's 1/, I can use a negative exponent. And then at that point, it's pretty clear that x is -3. Or again, not wrong to work in this spot to recognize that's 10 to the -3rd. And then log base 10 cancels exponent base 10 and you're out of there. So far, so good. Everybody kind of remember doing your log stuff. Won't see much of it in this class. Just a little teensy bit. 10 to the log of 6. What's this?
6.
Yeah, you got it. That's right. So again, you can write this as an exponential equation. Use your definition of logarithms to scoot it around. And look at that, x has to be 6 because the logs on the outside are the same, so the stuff on the inside has to be the same, right? Or you could just think, log base 10 or exponent base 10 cancels log base 10, and you're just left with the 6. I think it's easier to visualize, like that's more practical than doing this switcherooski. But this is helpful at times too. Like it's not bad, it does the same thing. But if I'm like trying to burn through a bunch of problems, like I'm using the idea of canceling log bases and exponent bases, and that's to me quicker for me to just grind through mentally than doing all the rearranging. Although it's not wrong to do it that way. All right, log of x equals 4. Yeah, the mental math here is not going to work, is it? So if we try to do this, we observe, okay, that's log base 10. We do our switcherooski. So there, x is just 10 to the 4th, or, 10,000. A little less natural to see that one from a mental math standpoint. Log base 2 of x is equal to 5. So same idea, right? So it should be 2 to the 5th is x, and 2 to the 5th is 32. The computer people in there probably, in the class, probably recognize that. Those powers of 2 are common in computing. Most of your memory numbers are built around those. I think last idea in the logarithm section is this change of base formula. Now, for you guys that exist in 2026, the change of base formula, not real important, because your calculator has that log base command on it, where you can just type in the log of any base and just press enter on your calculator and it spits it out. When I was a student, the calculators, you're lucky to have a calculator with a common log on it. You certainly did not have calculators with log base commonly available. So what we ended up doing most of the time, when we had to do a logarithm in class, is you flip to the back of the textbook. In the back of the textbook, there was a table of logarithms, like whole numbers down one side and decimal points down the other. You have to trace down and find, like, oh, log of 5.7. So it's like this number here, and then log of 6. Okay, it's that number there, and then I have to type in to do log base 6 of 5.7. I had to look up the values, type them into the change base formula on my calculator, do it manually. You guys don't exist in that world anymore, though, so this is typically not real important as long as you know how to use that log base command on your calculator. And I think at this point, nobody's still working with a calculator like an old enough operating system TI calculator that doesn't have that log base command on it. If you do, though, let me know and I can remind you. Worth pointing out that when we do this change of base formula, you can choose any base for your logarithms. The standard practice is to either choose the common log or the natural log, because your earliest generations of calculators that had log commands had those 2 log commands on them. But there's no reason why you couldn't use log base 26 or log base 5.2, something insane. Like, there's no reason you couldn't do that. I don't know why you would, but you could. All right, so if I do this, log base 3 of 16, I can just rewrite that as natural log of 16 over the natural log of 3. Type that in my calculator, press enter, or just use the log base. Got it. Done. All right. That's it for today as far as I am concerned. You guys can spend the remaining 40 or so minutes working on the first book homework assignment, which is going to be pages 23 to 26, numbers 1 through 20. I have copies of the textbook here. Go ahead and grab one. You're free to work together, talk amongst yourselves. All the answers for all the problems in that textbook are in the back.
Thank you. Everyone like this.
I'm gonna,
Textbook or what?
if you go to the Mind Ordained, there's a digital version. Now, I want to caution you, though, about the answers in the back of the book. This textbook is one of the most poorly edited textbooks I've ever seen. And I would say that answers in the back of the book are correct probably only about 85% of the time. And some chapters it's more like 50% of the time. Where it became pretty clear that like they wrote the textbook and somebody did all the answers and put them back there, then they went and edited the questions and changed some of the questions and didn't change the answers in the back of the book. Because some of them are not even close, like an insane person. I'm like, what is this number that you have in the back of the book? It's not even, it's so impossible to be laughable. So I just want to caution you on that back of the textbook. If you're like, this is not the answer that I got, but like, I don't see how I could possibly have been wrong on this. That's very possible that it's just the back of the book is wrong.
What was that homework pages? 23?
Yeah, 23 to 26. It's like the pink set of questions. They're like in a big pink box that goes on for a couple of pages. They should be relatively straightforward. It's just like, you know, like do a calculation around it, or like do a calculation, check the percent error, you know, or like do some rounding and write the bounds, or this number is rounded this way, what are the bounds? You know. So it should be relatively straightforward stuff.
What numbers did you say?
1 through 20. And that same assignment is listed on Minor Name if you wanted to go check. It's already in the assignment center or whatever.
Can I go to the library to check out
Off my desk, if you leave me your ID, that works for you.
I left mine a little bit.
That happens, that's why we got extras.
Journal thing.
Thanks for grabbing me.